Let's look at an example of a regression with multiple explanatory variables. We're interested in the effect of student characteristics and behaviors on test scores. So the dependent variable in our regression is the test score on the final exam, and our independent variables are number of class sessions attended, prior GPA, and the percent of homework assignments turned in, which is a value between 0 and 1. So our population regression function would be final test score for student I equals beta 0, the intercept, plus beta 1 times their number of days of attendance, plus beta 2 times their prior GPA, plus beta 3 times the percent of their homework that they turned in, plus their residual term U sub I. As we know, this translates to the following sample regression function. Now let's say we actually get a sample of observations and run this regression and get the following output. Using the mechanics of the previous sections in this module, we can interpret the coefficients as follows. For beta 1 hat, an additional day of attendance in class is associated with a decrease in final test score of 0.041 points, controlling for prior GPA and the percent of homeworks turned in. Beta 2 hat can be interpreted as an additional point in an individual's prior GPA is associated with an increase in final test score of 3.23 points, controlling for class attendance and percent of homeworks turned in. But this final coefficient is a little harder to interpret. Since percent of turned in homeworks is a value between 0 and 1, this coefficient actually measures the changes in final test score associated with the change of turning in 0 homeworks to turning in 100% of homeworks. So, to interpret this coefficient as it stands, we would say that a change of turning in 0 homeworks to turning in 100% of homeworks is associated with an increase in test score of 0.015 points, controlling for class attendance and prior GPA. Even if this is a mechanically correct interpretation, though, we are probably more interested in the change associated with a 1 percentage point change in turned in homework, rather than a 100 percentage point change. To do this, we simply divide our coefficient by the appropriate scale, which in this case is 100. So, this then translates to an increase of 1 percentage point in percent of homeworks turned in is associated with an increase in final test score of 0.00015, controlling for class attendance and prior GPA. Alternatively, we could translate this into a 10 percentage point change and say that a 10 percentage point increase in percent of homeworks turned in is associated with an increase in final test score of 0.0015, controlling for class attendance and prior GPA. Again, all three of these interpretations are both correct and equivalent. So let's look back at our previous coefficient. Since a change in prior GPA of 1 point is quite large, we might instead scale down our coefficient by 10, so that we can say that an increase in an individual's prior GPA of 0.1 is associated with an increase in final test score of 0.323 points, controlling for class attendance and percent of homeworks turned in. As long as we understand the units of our variables, we can translate our coefficients into practically useful findings.